All right, welcome back to the Kitchen Research Group. Today I have a new paper to tell you about. It's different than many of the ones we've talked about recently. This one is on a machine learning framework to find stable acidic water oxidation catalysts exhibiting lower levels of ruthenium dissolution. This was a big collaborative effort with Ted Sargent's group and NRC in Canada, with a lot of authors here. Rohan, Yuri, Sandsper did the work in my group, and we did this collaboration with Zach Ulysses, who's now at Meta. And this work was funded by NRC in Canada and Circuit Canada and the Army Research Office here, and is published in JAX. All right, in a nutshell, the problem is we want renewable hydrogen, and to do that we often split water into hydrogen and oxygen, and the current state-of-the-art membranes based on Nafion are acidic, and a lot of metals dissolve under acidic conditions. And so in the standard one that people use for oxygen is iridium oxide. It's very expensive, but it's also stable. And you can go down to ruthenium oxide. It's also expensive, but quite a bit less expensive, but it's also less stable. And so there need to be some strategies to make more stable ruthenium-containing electrodes for water splitting to enable hydrogen production at lower cost. So in this work, what we did was use a machine learning tool to screen 36,000 mixed metal oxides. And so we took the ruthenium oxide as the base crystal and then put different metal components in it to evaluate them for stability using the ML model. We found this particular one containing chromium and titanium that seemed to be promising. It was synthesized experimentally and characterized in a lot of different ways, and the experimental results showed that it was more stable and more active than ruthenium oxide. So I'll walk through the main parts of the paper. You can find it online, and there is a link in the video description. All right, so the ML workflow is pretty straightforward today now. This work's been going on for several years. And so we use this CG-CNN framework, and that is a graph neural network that has crystal graph convolutions in it. And so we have this system where we can make a metal oxide template, we can build supercells, we can substitute some elements, calculate with DFT some energies, and turn that into an electrochemical stability through a simple Pourbaix energy model. Then we have the graph convolution model here, where we use GNNs to generate features. Those get pooled into a crystal representation into a neural network, and that gets trained to predict these Pourbaix energies. And then once we do that, we can screen through thousands and thousands of possibilities to find systems that are more stable than ruthenium oxide. So once we do that, we filter them and pick the candidates that are the best. We found a bunch of candidates with titanium, tin, germanium, and chromium were found to improve stability. And then we applied some judgment from experimental knowledge in the past and things that we knew were likely to work. And we focused on the titanium-chromium system kind of going forward. So we made these materials. I'm using we in a very generous way. Our collaborators in Canada made the materials. They did all the synthesis and characterization using Soljo synthesis at different compositions. We did things like X-ray diffraction, spectroscopic characterizations, here Zanes and XAFs to look at whether we have single phase, multi-phase, how well mixed are the atomic constituents, and what kinds of oxidation states and so forth are they in. And then they did a bunch of electrochemical tests as well. So we have things like sweeps of current versus potential, where you can see the different materials that come in here, some kinds of Tafel slopes over here, some mass activity, and down here in the bottom right is probably the most exciting result. This is a stability looking at the O2 Faradaic efficiency, which you can see is quite high for these. But you can see the undoped ruthenium oxide dissolves very fast, and the other ones here are much more stable. And so we get a big improvement in stability by making this mixed metal material, and this is over a 1,000-hour test. So that's a quite big deal to have high activity, for example here, at low overpotential for 1,000 hours. All right, so in conclusion, we have used very successfully this ML-aided computational pipeline. I'd say this helped us narrow to a compositional space where we could search for an improved catalyst. And so we really narrowed down to a very specific region of titanium-chromium space, and then could finish the search with experimental work in that area. These mixed metal components lower the overpotential and improve the stability of the ruthenium atoms. And we found a particular titanium-chromium containing composition that was more stable and more active than ruthenium oxide. So again, link to the paper is in the video description. Hope you enjoy it, and we'll see you next time.